Welcome to the Transistorium and the very first video of this channel. What you can see here is a 4-bit full adder that I built on a breadboard. What it does is add two 4-bit binary numbers that are set here through these dip switches and display the result via these 5 blue LEDs on top here. I'll quickly demonstrate how it works. You can see it's connected to a 5-volt power supply here. If I switch the dip switches here, the result is displayed in real time, so to speak. So we set this one to 1, so the result is 1. I switch this one to 1 as well, and the result in binary is 0, 1, which is 2 in decimal. If we look at some more complex results, let's say we add 5, which would be 1, 0, 1 in binary, and 8, which would be 1, 0, 0, 1. The result in is 13 in decimal, and in binary that's 8 plus 4 plus 1 is 13. The 5th bit we need when the result is more than 15, because with 4 bits we can cover decimal numbers from 0 to 15. When we go over that, we need a carry bit to display 16. So let's say we add 6, which would be 1, 1, 0, and 11, which would be 1, 0, 1, 1. So the result in decimal is 17. So we got the 5th LED here represents 16, and we got the one which is 17 in total. My motivation behind building this was to get a better understanding of how computers work on a very fundamental level. I have a few vintage computers that need repair, and I set myself the task to repair them myself. So when I did some research on how to best approach this, I came to the conclusion that if I want to be able to repair these computers, I should first fully understand how they actually work. I then found this video by Ben Eater in which he explains just that extremely well. Basically, when adding two binary numbers, the first bits of each number and potentially a carry bit are fed into a series of logic gates that form a so-called full adder. The output of that is the sum of these two first bits, which is also the first bit of the resulting binary number, and the new carry bit if necessary. The sum and the new carry bit are then fed into a second full adder to calculate the second bit of the result, and so on. So if you connect 4 of those full adders, as we've done here in this example, you can add two 4-bit binary numbers, but you could add more, of course, 8 for 8-bit numbers, and so on. I won't go into too much detail here. Instead, I'll link to Ben's video in the description so you can watch it for yourself if you want to know more about the digital logic behind this machine. In Ben's video, the digital logic behind the full adder is very well explained, but it doesn't go into too much detail about the building of the circuit on the breadboard. It actually took me a while to get mine to work, and in the debugging process, I actually added a few components, mostly resistors. But let's have a look at the components on this breadboard. You've seen the dip switches, which are used to set the binary numbers that we're adding. These 5 ICs here come with all the logic gates that are needed for our 4 full adders. Each chip includes 4 logic gates. This one is for AND gates, 4 XOR gates, another for AND gates, another for XOR gates, and 4 OR gates. The pin layout of these chips is the same for all of them. This first chip here on top is VCC, which connects to the power rail. Ground is in this bottom corner here, and then we've got the 4 gates on the remaining pins, so input A, input B, and output. And then you just wire them up as per the logic diagram, and it should work. As I've mentioned before, compared to what I saw in Ben's video, I made a few modifications to ensure all is working fine. Firstly, I added resistors to the LEDs just to make sure they don't burn out. And I also added pull-down resistors to the pins to which the dip switches connect. Those are these resistors here. Without these pull-down resistors, the pins are floating when the dip switch is open. And at least in my case, there was enough voltage on them for the IC to interpret it as high, when in reality it should be low. There's one more thing that's worth mentioning, and that wasn't quite clear to me after watching Ben's video. You need, as an input, you need a carry bit signal for the very first full adder in the chain. But there is, of course, no incoming carry bit because there is no previous full adder. So you can connect that first input directly to ground, so it's always low. Okay, I think that's all I really wanted to talk about in this video. I hope you enjoyed it and maybe found it useful. Any questions or feedback, leave me a comment, please. I've done some more research and I have seen that you could show the result of the addition in decimal by using a converter IC and a display. I'm planning to try that out and show it in the follow-up video. Until then, thanks for watching. See you in the Transistorium.